A tiny mouse moves silently through a deep forest with no moonlight. To human eyes, the dark ground is completely black and invisible. Its physical eyes cannot form any useful image of the mouse. Yet a rattlesnake slowly turns its head toward the animal's chest. Then, the rattlesnake strikes with incredible and explosive speed. The sharp fangs reach a warm body the snake cannot see. It hunts successfully with a sense beyond ordinary vision. Between each eye and nostril is a small, hollow sensory chamber. This specialized pit cavity contains no lens and no retina, but it can detect the invisible heat released by living prey. How can a snake turn tiny, subtle changes in temperature and into a thermal image accurate enough to guide its attack? Only certain species of snakes possess this extraordinary sensory ability. Pit vipers have one deep facial pit on each side. Many pythons carry rows of smaller heat pits along their lips. These highly specialized facial organs detect invisible infrared radiation. Every object warmer than absolute zero releases infrared thermal energy. A warm mouse gives off more heat than the leaves. This creates sharp thermal contrast even when no light remains. But the snake is not seeing this heat with eyes. Instead, infrared radiation enters the pit and warms a membrane. This extremely thin membrane is suspended inside an air-filled chamber. The temperature change can be only a few thousandths of a degree. This minute level of heating raises a significant sensory problem. The thermal signal reaching the membrane is very faint and blurry. How does the snake separate its prey from the background? How does it use this signal to aim so precisely? Researchers examined the dense nerve fibers covering the pit membrane. They found that these fibers belong to the trigeminal system. This system normally carries touch, pain, and temperature information. These specialized nerve endings contain unusually heat-sensitive ion channels. When infrared radiation warms the membrane, the channels quickly open. This sudden opening changes the electrical activity of the nerve. The resulting electrical signal then travels toward the snake's brain. In this way, the pit behaves like a pinhole camera. Radiation from different directions reaches different parts of the membrane. This localized absorption produces a low-resolution thermal pattern. Thousands of noisy molecular sensors must be constantly combined. Only then can the snake reliably detect the tiny warming. Recent scientific modeling suggests that the nervous system improves sensitivity. It achieves this by integrating signals across many nerve fibers. Controlled experiments also show that infrared sensing directly improves hunting. These pit vipers can orient toward warm targets in darkness. But when both facial pits are blocked, targeting becomes unreliable. The major reveal is how the brain combines two maps. Signals from eyes and pits eventually converge in the brain. They meet in the optic tectum to direct attention. Visual brain neurons report exactly where visible objects appear. Meanwhile, Thermal neurons report where warm objects are located. Remarkably, some specialized neurons respond to both inputs simultaneously. This allows the snake to align a faint thermal target. It can then guide the exact direction of its strike. The result is not a colorful, detailed thermal camera image. A biological pit organ contains no millions of pixels. The thin membrane receives overlapping radiation from many different angles. The snake likely experiences a coarse map of temperature regions. But an ambush predator does not need high-definition details. It only needs to locate the warm center of mass. It judges direction to launch its head before escape. The soundscape features a rising, high-tension drone that builds through. The paired facial pits provide slightly different information from sides. Small movements of the head further change the thermal pattern. This helps the brain refine the precise location of prey. Heat sensing does not replace the snake's ordinary vision. It adds another sensory layer that works in complete darkness. However, infrared sensing is powerful only with thermal contrast. A warm animal stands out against cool nighttime soil. But on a hot rock, the thermal contrast is weaker. The invisible loss of heat becomes an inescapable target.